might be much more informally, that you ask questions orally as you're walking around the room.
Welcome to Literacy and Numeracy Secretariat's webcast entitled Differentiating Mathematics Instruction. We are pleased to have you join Dr. Marion Small in a Grade 2 classroom. Dr. Marion Small is a former Dean of Education at the University of New Brunswick. She has been a professor of mathematics education for many years and is a regular speaker on kindergarten to grade 12 mathematics throughout Canada and the U.S. The main focus of her writing has been the development of curriculum and texts for students in mathematics. Dr. Small has designed and led research about examining students' mathematical understanding and ways of knowing in each of the 5 mathematical strands for the kindergarten to grade 8 level. Most recently, she has also developed materials, conducted research, and provided consultation focused on differentiated instruction and teacher questioning.
We're going to try another question now.
I've been lucky in the last little while to get a chance to go into a number of different classrooms and see what's happening in mathematics lessons. And I notice that when I go into a classroom, you get a vibe, you get a feel that one classroom is kind of different than another one. And I started thinking about what are the elements that make a mathematical environment in one classroom sort of different than the environment in another classroom. So you start articulating, so what are the little elements that do impact? One of them is whether the math that students are engaged in seems like it's really rich mathematics, or it's very much a lot of skills and you're just practicing and not very significant mathematics. So it's the kind of task that students are doing in the sense of its importance. One of the things I notice is that some teachers have thought quite carefully about the words that they use to explain ideas or to summarize what students say, but they're very, very careful about their choice of words, kind of knowing that the way I say something might really impact on a student's ability to understand what I actually mean. The teachers who I found amazing would respond differently to one child than another child because they knew those children so well. They knew what kind of response one child needed versus what another child needed. And those needs are both emotional or psychological or whatever you call it needs, and also cognitive needs. This kid needs this kind of approach. This kid needs this kind of approach. Or this child needs this type of reinforcement from me. And this child likes it if I challenge him, and this child likes it if I celebrate what he did and then go on softly to challenge him. I noticed that some teachers, more than others, attend to the fact that because there's such a spread of student interest, ability, whatever in their classroom, that it's critical that they take that into account when they assign tasks for students to do. And they do it a lot of different ways. I'd also see a teacher whose focus was on what the kids were thinking instead of looking at her notes and figuring out when are they going to say what I want them to say. There are teachers who are much more attuned to what their kids are thinking, saying, how they're responding than other teachers. And in those classrooms, you could actually see that the teacher was spending time deciding, is what I'm doing right for these kids? Or seeing that, you know, I thought it was going to be right, but it wasn't quite right, so what am I going to do about it? And all of that made you wonder, how do teachers figure out what's right for the kids in front of them? And that led me into a whole nother research direction. I've had an opportunity over the last few years to do a lot of work on differentiating instruction, and the way I got to that was to actually look at development of students along learning continua in mathematics. So how do they develop in number, how do they develop in probability, and how do they develop in geometry, and so on. And we undertook a very large research study to talk about how kids are different in various ways. It gave us great language to be able to talk about the differences among kids, because sometimes we just say, well, this kid is struggling and this kid is doing well and this kid is doing okay, but that doesn't really give us a lot of information. So one of the things we did was try to articulate what the differences among students are. And the purpose of that articulation is to be able to, for a teacher to say, okay, well, if a student is here and they're missing this kind of thing, then these are the kinds of things that I do. In the course of that articulation, we actually noticed what some differences among students are. But before I actually talk a whole lot about the cognitive differences mathematically, I did want to talk about some other differences among students that I think actually impact how we have to differentiate instruction and how we see kids as being different and how we have to meet those kids' needs. One of the differences is how fast kids are. We have kids who get things fast, who actually perform quickly, and we have students who are slower. I worry sometimes that we actually say that a student is struggling just because they're not fast enough, and I think maybe that's a sad route to go down. I think that maybe we actually close doors to kids. We make kids feel less successful when we're looking at speed as a testament of how much you're struggling or how much you're not. There are easy fixes for that, and one of the things teachers can do, of course, is to not expect instant answers and to give questions that do require some thought, and kids will expect that it will take a little bit of time to answer. That leads me to another thing, which is the issue of what I would call perseverance. We worry when we give students a task and they don't get it and they immediately stop. They don't even try because they didn't get it. They figure, if I don't know right away what the answer is, I'm not going to get it, and so why even try? And one of the differences among kids is how much they're willing to persevere. Now, teachers have a big role to play in helping kids see that perseverance pays off, and part of that role is to actually give them tasks where they really see that happens. So if you give them a task, and even if you gave them an hour, they're still not going to get it. That's not going to help. But if you give them tasks where if they took the 15 minutes, they really are likely to get it, then that really is something that would help negotiate the differences among kids in terms of perseverance. Another difference among kids is what, I don't know what the real word for it is, but I call it a level of conformity. Teachers, most people are conformists. That's what conformist means. And teachers often have an expectation of conforming. So they actually think that a student should be thinking the way I'm thinking. And when I ask a question, I kind of expect a certain kind of answer. So when they see students giving a different kind of answer, they start thinking, well, the kid's not getting it. That student is struggling. I've got to help him. And one of the things that we need to do is recognize that conformity maybe isn't the end goal. Maybe conformity is a fact, and lots of kids do answer things the same way, but in fact, a kid who answers differently may actually be thinking in a very critical way, a very important way, a very meaningful way, and we just don't recognize it. So the level of conformity should never be the factor that makes kids successful or not, but it is something you have to take into account when you're planning your instructions, because you have to allow for that difference when you're trying to differentiate instruction. And the big differences are, in fact, in terms of their mathematical sophistication, and that's something I spoke to a few minutes ago about the research that we did in terms of levels of mathematical sophistication. We find that certain mathematical operations are more difficult for kids, but interestingly enough, not initially. So initially, the kinds of simple situations that involve adding or subtracting or multiplying or dividing seem equally easy for students, especially if they have manipulatives in front of them and they can actually model the problems and count them out. So for example, saying that there's 2 plates with 3 cookies each, which is multiplication, is not really any harder for a kid than saying she has 2 and he has 3, how many do they have? So it's not like multiplication is harder than addition. What's interesting is that later on there seem to be big disparities, and some kids just kind of close down when you get to division, or close down a little more with subtraction than addition. And those are things that teachers have to take into account when they're trying to decide how to change the instruction they planned, or how to plan for the next day, or how to think about what to do next. In the pattern strand, we also found differences among students. So one of the differences is that students who are pretty good with patterns that we would call growing patterns all of a sudden have a lot more difficulty with shrinking patterns. So if you ask them 1, 3, 5, what comes next? No problem. You ask them 42, 40, 38, what comes next? Well, then that's a problem. And we actually suspect that part of that might be our doing, that we don't actually give them very much experience with those kinds of patterns, so they have difficulty with them. Now, I mentioned pattern and I mentioned number. In each of the strands, whether it's data or it's probability or it's geometry or measurement, there are other kinds of differences among kids. So for example, in the data strand, one of the differences among students is their ability to look at, say, a graph and do more than just read it. Maybe they have to look at it and put together some ideas from what they see to make an inference. And we have some kids who can make those inferences and some kids for whom that's quite a struggle. So they might look at a graph and say, how many kids like summer better, how many like spring better, how many like fall better, whatever it is. And if you say, well, how many do like spring better, they can look at the graph and they can tell you how many. Then you say, so when should we have this particular activity? And they don't really know how to use the graph to help them make this kind of inference. Our goal with data management is, in fact, for kids to make inferences. It's not really for kids to read graphs. It's for kids to interpret, well, what does that mean and what conclusions can I draw? And we know that kids are quite different in their ability to do that, and the teacher who needs to do that to meet curriculum expectations needs to start thinking about, well, how am I going to adapt that task to help that other student? Data management is also interesting because we make graphs or we collect data or we draw inferences about things in the real world. And yet our students come from many cultural situations, from many environments where their experiences might actually differ. And if we talk about pets, for example, and a student has just come to Canada from another country, and the whole notion of what is a pet or what isn't a pet is totally foreign to them, then how do they participate? How do they fully engage in the task that you're trying to do? And that's another way that teachers need to start thinking about how kids might be different. How do I pick tasks that suit this range of students who's really in front of me that are about data that will be meaningful for those particular students? Probability is a strand that's an interesting one. When I went to school, probability was something you did in high school. Now we actually start it in grade 1, but we're doing some simple ideas. We're not being too abstract. We're not being too numerical. Yet at some point, we do have to have kids talk about the probability as a fraction or a ratio. We find that's a real barrier for some kids. So if you talk about things that are probably going to happen or likely to happen or certain to happen, they're fine. If you talk about the probability is 5/6, they're not so fine. And in fact, we even find a difference between kids who understand the idea of 1 out of every 2 being, that's okay, but as soon as you say 1/2, it's not so okay. Or something will happen, you say 3 out of every 4 times, that makes sense, but as soon as you say it's 3/4 of the time, somehow, for some reason, that seems too abstract to them, it makes a lot less sense to them. The teacher who is charged with helping students write probabilities as fractions needs to deal with that. What am I going to do if somehow they really do understand the ideas, but what they don't understand is writing it as a fraction? How am I going to make that make sense to them? How am I going to bridge back to what they already know so it's meaningful to them? One of the important notions in probability is that when you're going to use numbers to describe probability situations, You need to consider how the different how the different things can happen and whether they are what we call mathematically equally likely. So for example, if you have a big spinner and there's a 1 on it and a 2 on it, and the 1 and the 2 are the same size, then it's equally likely that you'll spin a 1 or a 2. And kids kind of understand that intuitively. And if you have a big spinner and there's a tiny little 1 section and a great big 2 section, kids kind of know you're going to spin a 2 more than you're going to spin a 1, and that makes sense. Sometimes when we get slightly more abstract, it's not so clear whether things are equally likely or not. So for example, we ask a child, if I flip 2 coins, is it as likely that I'll get 2 heads, 2 tails, or 1 head and a tail? And it kind of does sound like those should be equally likely, because it's all the things that can happen. And yet mathematically, it turns out that one of those things, in fact, the 1 head and 1 tail, is actually more likely than the others. That's a really tough sell for some kids. The teacher who needs to teach that kind of idea really needs to think about, how am I going to approach that so it makes sense to a student for whom that idea is foreign. One of the most interesting things we found about probability, for me it was definitely the most interesting thing, is how most of our work in other mathematical things messes up our work in probability. And what I mean by that is that we spend a lot of time in number, in pattern, in measurement, in geometry, of helping kids see how much pattern there is in math. Everything's a pattern. When you count, there's a pattern. When you multiply, there's a pattern, whatever it is. And probability is the absolute opposite. Everything is what you call random. There is no pattern at all. So what happens is, if a kid flips a coin and gets head, head, tail, and you say what happens, what's going to happen next, and you want them to say, I don't know, they don't say I don't know. They figure if it was head, head, tails before, it's going to be head, head, tails again. And all of our work in all the other strands actually seems to kind of debilitate kids in probability and really causes some difficulty for a lot of kids. Our research also looked at the other strands, geometry and measurement. So I'm not sure how many of you are aware that in geometry there actually has been a continuum that's been around a while. It's called the Van Healy Developmental Continuum, and it articulates how students grow geometrically. We were looking at that continuum to see if we saw it at the elementary grades in which we were looking, and to see and to actually refine it a little bit to see how we saw it playing out. And one of the things we uncovered was indeed that we did see aspects of the continuum. So for example, we see kids first going through a phase where they don't really look very deeply at all the properties of a shape. They just kind of see, well, it's a triangle because it kind of looks like a triangle. It's not because it has 3 sides and 3 angles. It's because it looks like a triangle. And that is something that Van Healy talked about, and that is certainly something that we saw. Many of you in your university days heard about conservation and Piaget and all that stuff. And so one of the things that you're probably well aware of is that there are kids who conserve a measurement and kids who don't. So there are students for whom, if you take a string and you hold it and say, how long is it, they'll come up with a number, and then you move it and say, how long is it now? They'll actually think it possibly could have changed. And then you have kids who know that it didn't change. And in fact, measurement is all about kids sort of depending on the fact that the number didn't change. You couldn't say that the area of a rectangle is 12 units if it was going to change if I pushed it over. Then you wouldn't know what the area is. So a lot of our measurement work is built on students having that belief. We know that there are a lot of young students and sometimes slightly older students who don't have that belief, and that's something teachers have to deal with. We found that one of the things that some students struggle with more than others are what I would call measurement, I think we call them conversions. So I'll tell you how many meters it is and you tell me how many centimeters it is. Or I'll tell you how many kilograms it is and you tell me how many grams it is. And we have kids who are quite different in their ability to deal with conversions. We have students who are fine if you start with a big unit and go to a little unit, but not so much the other way around. We have students who are fine if they're linear units, for example, going from meters to centimeters, but they're not so great if it's square meters to square centimeters. And in fact, that's a very difficult thing for a lot of students. We found differences in students in their ability to use formulas in meaningful ways. So we find that a lot of students understand that a formula is a shortcut to to do a measurement. It's not different, it's just a shortcut way to do it. So if I have a rectangle, it's just easier for me to measure how long and how wide it is than to actually fill it with squares and figure out what the area is. So if I know the formula, that's really cool and I have a way to do it. We have kids who really understand that's what a formula is. We have kids who don't. They may even be able to use the formula in the sense that you give them numbers and they'll plug them in and it works, but they really don't get what they're doing and really don't see the power of the formula, and from that perspective really haven't internalized what our purpose was in instruction. We also have kids who don't use what they know in one situation to help them in another. So for example, if I were looking at the area of a rectangle and I add a little piece to it and say, what's the area of the new shape? You have kids who realize that all I have to do is find the area of the new little piece, add the two numbers, and I'm done. You have other students who think, okay, I better start all over and go from the beginning. And those students, it's not that it's a bad thing that they did, but they're in a different place in terms of mathematical sophistication. When you handle them, you have to accept that difference, and you have to give them opportunities to grow so that they can actually use what they learn in one situation to help them in another. A lot of teachers these days have been picking up books that talk about what differentiating instruction is all about. Some of the books talk about something called differentiating process, product, and content. And sometimes that sounds pretty good. So differentiating a process might be that you'll let a student use one manipulative versus another manipulative. Or differentiating a product might mean that you'll let a student answer orally versus in writing. And those are probably useful things to do. I think what we haven't done very well is differentiating the content, and by the content I mean recognizing that students need to deal with the same big ideas, but they need to deal with them at different levels of mathematical sophistication. And so you have to be kind of aware of what those different levels are, and you have to be aware of what those big ideas are that actually can cross those levels of sophistication so that you can meaningfully deal with all the students in your class all at the same time, but meet them where they are rather than expecting them to be where you want them to be. Now, when we go forward in this conversation, I'm going to focus on two big and important strategies, and I'm going to come back to them in different ways, that you can use to differentiate instruction in terms of teaching the same big idea, but meeting students where they are. One of them is about being more inclusive in the kind of question you ask by making it open-ended enough that all students can participate in a meaningful way in that question. And the other way we'll talk about is using what I would call parallel tasks, tasks that are about the same big idea, but meet students at two different places, and this one is going on and this one is going on, and they're so close that when we talk about them, we can all talk about them together, but in fact, this is suiting the needs of one student and this is suiting the needs of another student. One of the things that's interesting is that the very same elementary teachers who teach literacy and math feel quite differently about the possibilities of using these strategies in literacy and in math. So in literacy, teachers frequently will recognize that students are perhaps reading at different levels, and that the kind of book I'm going to give to this student should be different than the kind of book I'm going to give to this student, even though both of them are doing important literacy work. The same really is true in math. It's just that we don't have a history or a culture of doing it. So it's a little bit surprising that in math we don't feel so comfortable giving students this task and giving these students this task and letting both things happen at the same time and kind of finding a way to talk to both of those groups mathematically in some kind of meaningful way, even though the tasks they were doing are different. Now, if you're going to use these strategies of differentiating instruction, one of the things you need to do, of course, is to find out where your students are. We call it lots of different things. Most of you have heard the language of assessment for learning, and sometimes people break that out and talk about what they might call diagnostic assessment. So before I actually start a piece of instruction, I actually want to find out where my students are relative to this content area that I'm going to teach. And I thought what I'd do is give you an example of what it might look like and show you the possibilities and the actual richness of the possibilities for diagnostic assessment. And I decided to talk about grade 2, and we're going to look at what we want students to be able to do in grade 2 in terms of addition and subtraction, and how we might gather information in advance to find out where our students are so we know whether they're ready for our instruction. There are actually only a couple of expectations about addition and subtraction in grade 2, but they're big and important. So we want, for example, students in grade 2 to be able to solve and create addition and subtraction problems with numbers of a certain size. And we want them to use a variety of tools, and those include different kinds of concrete materials. We want them to use a variety of strategies. We want them to create their own algorithms. So we want, it's one little expectation that's very big and important, and is certainly going to take significant time to develop. One of the other expectations that's relevant is the ability to work with coins and money amounts with those same kinds of numbers doing similar addition and subtraction problems. And clearly money is a context that we use for some of those things. So let's say you want to get students to that place. What you're going to need to know is what should they know beforehand in order to get there, so I can find out where they're at and to find out how successful I'm going to be moving on. One of the things you might want to know is whether you're wasting your time. They already can do it. So teachers might use a task that finds out, can students already do what it is I'm planning to teach them? And that would be obviously important information. If we're talking about addition and subtraction, you might want to know, how do they do with what we call the facts? They're single digit additions or subtractions. So do they know 9 plus 4 is 13? Do they know 16 minus 9 is 7? Because if they don't, then we're going to struggle when we're doing work with 2-digit addition and subtraction. You might want to know if they know in which situations you add and in which situations you subtract. So for example, subtraction is actually a pretty complicated operation. We use it in many different ways. We sometimes use it to figure out how much we have to add to a number to get to another number. We sometimes use it in what we call a takeaway or separating situation, where you have something and some part of it goes away somehow, or is used, or is lost, or is left, and you want to know what the rest is. And sometimes you want to compare, like how much more is one thing than another. Those are all very different meanings of subtraction, and you may have students who are good at one, not at the other, and you may want to know that because it'll inform the instruction that you're going to do with them in 2-digit addition and subtraction. You may be interested if they're good with the symbols. Do you know when you write the plus and when you write the minus, and how do you write the number sentences? You might be interested to know if they're familiar with the vocabulary you might use. So for example, if I say the word sum, do they know what I mean? If I say the word difference, do they know what I mean? You might get fancy and say the word addend or minuend, and do they know what I mean? And all of those would be important things to be able to have in your pocket, to know about your students in order to know how to proceed. You may want to ask questions to see how comfortable they are with 2-digit numbers, because if you're going to work with 2-digit numbers and 34 doesn't mean a lot to them, then very likely the work you're going to do is going to be problematic for those students. You may need to know if they're familiar with the coins, because if they're not familiar with the coins, then all those money problems are going to be problematic. How are they going to model 34 cents if they don't know a dime is worth 10 cents and a penny is worth 1 cent, and so on? You might be interested because perhaps these students are new to you and you didn't teach them in grade 1, and you might want to know, what materials did they feel good? What materials are they comfortable using? So for example, you may want to know if 10 frames are the way to go with these kids, because that's what's their comfort zone. Or it might be their familiarity with base 10 blocks, or it might be Unifix cubes that are linked to make 10s, or it might be popsicle sticks, or whatever it is. You may want to be familiar with the materials that are useful for them. You may be interested in, I don't know if attitudinal is the right word, but you might be interested in whether these students are likely to stick with you if they have a tough problem. It's what I called perseverance before. Because if kids persevere more than other kids, you're going to approach things differently with them. So once you know that this is all kind of information you want to know, and I know it probably already sounds overwhelming, and you may not choose all of those things to find out about, you may focus on some of those things. You have to then decide, well, how am I going to gather that information? And I guess in the old days, we thought you would give some kind of little quiz or something to gather, and I suppose you still could to a certain extent, but we really have many more options that are comfortable and familiar to teachers to use now. So one of the things you might use is what I would call a performance task, and we'll look at examples of each of those things. So you might have a performance test to find out where students are at. It might be to find out, can they already do these kinds of questions? It might be to find out if they can do previous things, but some kind of performance task. It might be, more likely in older grades than with grade 2, paper and pencil questions, although a grade 2 teacher might still have a few, can you add these numbers, 4 plus 2, what is it, whatever, and you might do a little bit of that paper and pencil. More likely you would ask those kinds of questions in an interview situation. So I'm going to sit down with a small group of kids and ask them a few questions to see where they're at in terms of those things that I wanted to gather information about. And when you're going to do these questions orally with kids, it might be in more formally in an interview where you've actually scripted some questions you're going to ask them. Or it might be much more informally, that you ask them questions orally as you're walking around the room, or even to the whole group of students. And all of those are possible ways to gather the information. So let's go through the kind of things you might do for each one. So I'm going to start with a performance task and give you some ideas of some options that you could use. And at the same time that we do that task and I give you those options, I'm going to kind of introduce you to the idea I mentioned earlier of using parallel tasks. So what I might do is I might post 2 problems for kids to consider on the board or on chart paper. And I might even say pick one of those problems to try to solve and see how students perform with that task. The task is not something that's done in a minute. It's something they're going to have to take a little time with. So that perseverance issue I mentioned before is at play. So you need to have established with students that they'll have the time to work on this thing. And what you might want to do is have one task that is actually a measure. Can students actually already do what I intended to teach anyway? And if they can, then I know that I want to change my instructional plan a bit. And maybe the other task that you give as an option is perhaps not as intimidating. It doesn't require students to be kind of at the end of where you want to go, but you kind of want to see, in this case, how are they doing with 1-digit numbers, because I want to see where they're at with that to see where we're going to go with 2-digit numbers. So you see the 2 tasks that I'm proposing that you look at. And you could offer both of those. You can see both of them involve thinking about addition and subtraction. They're slightly different, but they're both meaningful tasks to gather diagnostic information. So in one of the tasks, we have a bus problem where we talk about a group of kids, and we talk about how many students the bus holds, and we talk about how many kids are already on the bus, and we ask them how many more students the bus can hold. Now what you'll notice about that task is that it involves 2-digit numbers, because there's the 36 there. You'll also notice it involves both addition and subtraction, because kids have to figure out by adding somehow how many kids are already on the bus, and they have to figure out by subtracting how many more students could still fit on the bus. And there's many strategies students could use to solve that problem, and by watching those strategies you learn a lot about what those students are thinking. One of the things that you'll notice is that if students can do that problem, they really are pretty successful at where I want to take them. Now, I admit it doesn't mean they can do any 2-digit addition and subtraction, but it really shows you what tools they have to bring to bear to those kinds of problems and how far down the road they already are on that path. I made the other problem, the one involving the birthday cake and the candles, a simpler problem. You'll notice it involves using 16 candles, so the kids could use facts. So they might use 8 and 8, and they might use 9 and 7, and they might even use 10 and 6, which isn't technically a fact, but it really shows you what facts they can bring to bear. Now, it's facts involving teen numbers rather than earlier numbers, but it does show you what facts they can bring to bear. And it also shows you whether they stop after they have one combination or if they continue, and so it shows you a little bit about their perseverance as well.
I had to make the same number as the other one.
That's right. And so you came up with this answer, and what were you going to draw here?
6 plus 10 equals 16.
Good. If I asked you to come up with a 4th picture of 2 cakes, would you be able to do that too?
notice that you could talk to the kids about what they did, and you could probably have a communal conversation with both groups of kids and saying, okay, so tell me about the problem and tell me how you tried to solve it. And it really wouldn't matter which problem the students were working on. You could continue that discussion with both groups of kids. Now, I'm going to call that a contextual problem, and all I mean is that it's kind of real worldish, that you're using the math to solve what I would call a real world problem. Now, we have been advocating for the last while that we use lots more context and that we make more of our problems meaningful to students by using context, but sometimes we still use more purely mathematical context, but they can still be engaging for students. So you'll notice here I'm showing you a different situation. We have this little beanbag game that students are playing, and they get to throw beanbags, which is already fun for students, and they have to do some addition and subtraction in order to solve the beanbag problem. So the way the problem works is they throw, and presumably they aim to get certain numbers, and they have to do some additions and some subtractions. What I want you to notice about the beanbag chart that I have there, or what it looks like, is that I've particularly selected numbers so the kids have choices. They could aim at the one-digit numbers or easy numbers like 10, or they could aim at more difficult numbers like 42 and 28 to do their computations. They can be successful at winning the prize, which is what the game is about, whether they pick the littler numbers or the bigger numbers, but they get a choice. Now, one of the things that's, of course, interesting is because it's a beanbag game, when the kids throw, they may not hit what they aimed at. And so then you have kids who are actually struggling to figure out what to do, which isn't such a bad thing either. But it certainly gives kids options, and it certainly allows the child who's struggling to really try hard to get 10s and 7s and simple numbers for him or her so that he can be successful at the task and just as successful as the other students. I mentioned before that you might do some paper and pencil things. Now, I think with a grade 2, it's highly unlikely I do too much paper and pencil, but you might do things about gathering some information about facts they know, whether they can understand little equations, number sentences that you write, and so on. And that might be a reasonable thing with paper and pencil. I mentioned coins before, and one of the things you might want to do is show them coins on a picture and say, you know, how many cents is this worth, how many cents is this worth, and that might be a reasonable thing to do on paper and pencil for kids at that age to find out what previous knowledge they're bringing to bear. Frequently, we get our best information by talking to our students, and there's a lot of different ways to go to gather information orally. Certainly, I talked before about how you can just talk to kids as you walk around the classroom and have what I would call a mini interview, just asking a kid a quick question and getting a quick answer. We can have formal interviews. So if, for example, we were talking about this grade 2 addition and subtraction, you might do something simple like, so tell me if you agree or disagree that if you add two numbers that are more than 20, the sum can be less than 30.
Disagree.
Tell me why you disagree.
I'll pick a number from the 20s and the 30s.
Okay.
If I get 29 from the 20s and I get 31 from the 30s, so the answer would be 2. The difference is less than 10. And you could do more than 10, less than 10, or 10.
Well, I think I agree, and then they have to defend why they agree, or I think I disagree, and they have to defend why they disagree. And there's all kinds of really fun questions. They really focus on the reasoning process a great deal, where kids reason about why this might be true or not true. And so it's a way to highlight the reasoning process. It's a way to give them a measure of their success, and it's a way to get prior information about where students are actually at. If, for example, you decided I want to actually sit down with a child or sit down with a small group of children to find out what they know, then you might prepare for yourself a couple of questions that would structure your interview. And you would have thought about those things I mentioned earlier. What do I want to know about what students know? And ask them questions that are relevant.
Show me how to make 32. Can you show me with your manipulatives how to make 32?
So, for example, you might be interested to find out how familiar they are with coins. which is something I mentioned to you earlier, but you might also be interested in finding out how they can represent two-digit numbers. So one possibility is to say, here are some coins, and you can lay out pennies and nickels and dimes and quarters and whatever you want, and say, show me 43 cents. What does it look like? And in that way, you're gathering two pieces of information. You're finding out if they know what coins are worth what amounts, and you're also finding out if those numbers are meaningful to them. You might do something even simpler back with one-digit numbers. So you might be interested to see if you had colored counters, if they could represent some addition or subtraction situations. So you might say, here are 8 red blocks, and here are 5 blue blocks. How many blocks do I have? And you might ask them how they found out. And so you'd be interested in whether they told you that they added or subtracted, or whether they even used that vocabulary.
How did you know there were 13 blocks?
Because I knew that these, if I add another, if there's 5 over here, 2 5s, they make a 10, and these 3 1s make a 3, so it's 13.
Can you show me how you would take away 7 blocks? And how many blocks are left?
6.
How did you know how to take away 7 blocks so quickly?
Because I knew that 5, and I just have to take away 2, which makes 7.
So I mentioned to you earlier that the 2 strategies that I've been focusing on in my work in helping teachers deal with differentiated instruction are the use of open-ended tasks and the use of parallel or choice activities. So let me start with an open-ended task to give you a feel for what it looks like. Recall that when I use an open-ended task, I'm thinking, what's the big picture? What's the key idea I'm really interested in? What am I doing this for mathematically? And then I'm able to think of a way to allow students to participate at whatever level they are at in that activity. So here's an example. Instead of saying, hey kids, I have 3 and 4 and 6, so what's 3 plus 4 plus 6? Instead of saying it that way, or whether it's 2-digit or 1-digit or whatever, you can say, okay, what I want you to do is I want you to pick 3 numbers and that you're going to add them, and I want you to come up with a problem that would lead you to add those numbers and tell me what your answer is. Now notice by saying it that way, I can have kids pick really easy numbers. They could pick 1 and 1 and 1. They could pick 2 and 2 and 3. They could pick nice and easy numbers if that's where they're at. Or they could pick 1 million and 2 million and 3 million if that's where they're at. Or they could pick 22 and 34 and 15. But that question allows all of those students to participate. It allows all of them to recognize that you add when you're putting things together, because the problems that they're going to create are all going to be about putting things together, but they're going to be able to do it at their own level. What's really great about doing that kind of activity is that when you do it, when the students hear each other's work, the student who picked 1 and 1 and 1 is still hearing the kid who picked 15 and 20 and 35 talk about their problems. So they're really getting what we often call that opportunity to learn, that more sophisticated thing, but they're feeling success because they were able to make up a problem that they could handle. So they're successful, but they also have the opportunity to learn this new thing.
There are 7 lions in the cage, 8 lions sleeping, and 5 lions in the zoo eating. How many altogether? I took the 7 and took 5 and put it into the 5, and the 5 turns into a 10. So I take the 2 from the 7 and put it into the 8. That makes it into a 10. 10 plus 10 equals 20. So I ended up with 20.
In geometry, we could use open tasks certainly as easily, if not even more easily, than with numbers. So, for example, I might say to kids, I want you to take 4 squares and make a shape with them, any shape you want. After you've made your shape, I want you to describe your shape to me, And once you tell me about your shape, I want you to take that shape and think about what other shapes you can make with that one. And notice that some kids will pick one simple little shape they can make with 4 squares, whether it's a bigger square or a rectangle. Other kids will make a much more complicated shape, you know, a guy up here and a guy over here and whatever, and they'll describe their shapes. Every child in the class gets an opportunity to describe the shape they chose, not the shape I chose for them. Because our usual way is, I want you to take these 4 squares and make a bigger square. So what I'm doing differently this time is I'm not giving you my end point. I'm letting you pick the end point so that you're comfortable describing your shape, and then you're comfortable describing how your shape can make other shapes. Now, the reason I would give a task like that is that one of the most important ideas in geometry is how combining shapes gives you new shapes, or how breaking up shapes gives you other shapes. And all of those answers that those kids might give me bring that out, but they bring it out at the level at which the student is ready to work, not at the level that I'm demanding. Now, for the parallel tasks, when I mentioned to you before that the way those work is you have 2 different tasks going on. You might actually say to the children they can choose which task to work on, or you might suggest to a particular child or group of children to work on one task and another child or group of children to work on another. And you set them up so that when it's done, there's a conversation you can have with all the children, but you set them up thinking these kids can handle this, these kids can handle this, and I want them all to be successful. So for example, you'll see that the situation I've set up here is a money situation, and we've taken some very common items and given them little prices. And what we've said for one of the choices is that you have 50 cents. You're going to buy 2 items from this school store, and you want to know how much you would have left after you paid for those items. And for the other children, you're going to tell them to buy 1 item with 10 cents. So what you can clearly see is that both of them are working in the store, both of them are buying items. When you finish the task and you talk to all the kids, you can say to any of them, so what did you buy, and how much money did you have left, and how did you figure it out? But one of them is working at numbers they're comfortable with, the 10 cents and the 1 item, and other kids are working with numbers they're comfortable with, the 50 cents and the 2 items.
If you have 10 cents, you want to buy 1 item. If you buy a pencil for 8 cents, you will have 2 cents left. I know that 10 take away 8 equals 2.
The teachers who seem to me to be most successful with differentiated instruction seem to be the ones who, through experience, through professional reading, through dialogue with colleagues, can anticipate what kinds of responses students might give so that they're prepared and ready to work with students as they start giving those responses, and either move them further along a continuum or help them get back on track if they're a little bit off track. So one of the important things teachers can do is to take the time to figure out how to anticipate what students might do. And again, the best way is to actually try tasks and see what students do. And then to plan questions that you could ask afterwards to help the students. The kinds of questions teachers ask are really important. They make a huge difference to students, and often we call them prompting questions. And there are some what I would call generic prompting questions that are really useful, and you can see some of them listed here. So it might be who agrees with me, or it might be what was the easiest part of this, or it might be why do you think whatever it was that you said. And those are very useful generic questions. Often we'll ask a student to explain why they did something. So what did you do here, and why did you do that, and what would you do next, and what if this happened, what would you do next? And those are all good questions to ask and very valuable for a teacher to have in his or her toolkit. It's really helpful if you know the mathematics that you're teaching deeply enough that you can also ask specific questions that are really about that particular problem. Like, why did you decide to use the 8 first? Or why did you decide to do it in this order? And if you've anticipated strategies students might use, it really will help you formulate those much more specific questions, which are very useful as prompts. One of the things that you might be interested to know is there's been a whole lot of research on teacher questioning, and one of the things that research has told us is that teachers mostly question to check. Like, did he get it? Does he understand what I said? Does he understand my directions? And all those kinds of things. Teachers have seem to use less questions that initiate thinking, to get kids going, to keep them going. And so one of the things that would be very valuable for teachers to do is to kind of learn to use some of those initiating questions to get kids to go. And it's really important when you do those questions to have thought to yourself, well, why am I doing this? Mathematically, what are the kids going to get out of this? What is the important mathematical idea that I want to come out of this? And then that'll help me frame this question that will get them thinking. So let's look at this particular problem. A teacher might draw the shape that you see in front of you, and they might draw the dotted line, and they might say to the children, if I cut the shape on this dotted line, what will the two parts look like? And that's a perfectly okay question, but I want you to compare it with this question. Pretend that dotted line isn't there, and I say, what shapes can you create by cutting up this shape? Now, do you see how much richer that is? The kids could cut vertically, they could cut horizontally, they could cut diagonally, and the discussion that the kids are going to have is a much richer discussion. I'm focused on that key idea that when you take a shape and cut it up, you get other shapes, and that when you think about those shapes, lots of properties are valuable to talk about. And one of the things that we want teachers to be able to do is to ask these questions that are richer and initiate a deeper conversation. So again, the first question I ask you, cut on the dotted line, it's okay, but the conversation's going to be over. In a minute, it's over. Whereas the second one initiates conversation. And when you actually count the minutes of time in the classroom where you'd hear teacher voice versus student voice, if you ask the second question, you'll hear a whole lot more student voice. If you ask the first kind of question, you'll hear a lot more teacher voice. One of the things teachers often focus on doing is being clear to students. And that sounds very noble, that we want to make sure they understand us and so on. And I think it's a good thing, but I think maybe sometimes we carry it too far, because a little bit of ambiguity is actually helpful. It gives the student an opportunity to kind of see things a different way, see things his own way, contribute to the conversation much more than would be the case if we made it so narrow that we know every kid is going to think exactly the same way. So one of the things we've learned about questioning is that a little bit of ambiguity is kind of useful, not too much, but a little bit is useful to initiate a richer conversation. We also know, and I think this is more, our human interactions would tell us that when we can respond to a student in a much more personal way, it's more meaningful to that student. So if I ask a question like, what's 35 plus 22, and they say 47, and the kid says 47, and I say great, or the kid says 45, and I do something because the kid is having trouble, it's not terribly personal. If I ask a question, for example, if I did the geometry question like we did before, and I say, well, what shape did you do? And the kid says something to me, and I respond to that child in a very personal way, that I take his response into account when I give my response, we know that that's a much more important thing for the student. And truly, it's a way to differentiate instruction, because it's a way to say to that child, I am talking to you. Some of the most successful professional learning sessions I've been involved with have been involving teachers bringing in student work and talking to other teachers about what they would do when they saw that response coming from a student. And so I thought I'd share with you a couple of responses that I got in various situations. and give you an opportunity to think about how you might respond if one of your students said this. So look, for example, at this particular one where you have that shape that's sort of butterflyish, and you ask the students how they would find out if that shape has symmetry. And most of us are expecting the kid to say something like folded or something like use a mirror. And this kid says, I'd use a ruler. So what are you going to say? So think a minute about what you might say. And think about what a teacher could do. So I've actually seen teachers say, well, why would you use a ruler? And as soon as you say that, you've closed down everything. You've closed down students' interest. You've closed down students' willingness to try the next time. You've closed down everything. If you say, hey, that's cool, so how would you use that ruler? What would you do? That's a totally different way of responding to exactly that same response. That's inviting, that's telling the student, hey, I'm kind of interested in your response, what you would do. And in fact, it could be a really great response, because in fact, one of the ways we do decide if something is symmetrical is if the distances on one side are equal to the distances on the other side, and a ruler would be a perfect tool to do that. So rather than saying, what's with this kid in your mind and what am I going to do, you're thinking kind of positively, well, this could be a really good answer. What could I do with this answer? And often it's just saying, well, why did you say that? But in a very positive, friendly way. Here's another example. We have a pattern there for you to look at. So it starts with 3, 12, 21, and 30. And I'm betting that most of you who are looking at that, because we're all math teachers, are thinking, hey, that's obvious, you're adding 9 every time. And this kid says, after you ask them what the 10th number in the pattern is, that I think it's 12. And you're sitting there mentally scratching your head, like, why would they say 12 when what you're supposed to be doing is adding 9? But instead of being negative about it, you say, so how did you come up with the 12? And the student actually could have a really great argument. So a student might be thinking it goes 3, 12, 21, 30. 3, 12, 21, 30, 3, 12. And darned if the 10th number isn't 12, it makes total sense. So one of the reasons that we need to respond to students is because even though they're thinking differently than we are, it really might make lots of sense. Have a look at this particular situation. What I have are pictures. And remember, I mentioned to you before that there are some kids who respond differently to the real objects than to pictures. So in this case, I have pictures of a big pitcher and a little mug, and I'm asking them how many of those little cups it would take to fill the pitcher. So the kid says 2, and you're kind of wondering why the kid says 2. You're probably thinking that they don't understand. But remember, I mentioned to you before how valuable it is to anticipate student responses. If you had thought ahead about this, you might have figured out, some kids are going to say 2, because if you just look at the pictures, the big pitcher looks about twice as high as the little cup. So 2 actually makes kind of sense. So you're thinking about what would you say to the student, and it might be, so how did you get the 2? It might be, how would you test that idea? Like, okay, maybe it's 2. How are we going to figure out if it really is 2? And give the ownership back to the student to figure out, what are we going to do next? What are we going to do to make sense of this? One of the interesting struggles we have with fractions, and when we teach fractions, is the difference between fractions and ratios. In fact, we actually teach kids at some point that ratios and fractions are the same thing, but they're not really always quite the same thing. So we presented students with this particular picture. We have those 6 squares and we have 2 of them shaded, and we asked them to write a fraction for the part that was shaded, and the child wrote 2/4. Now, it's kind of pointless to ask them why they did it, because it's pretty obvious why they did it. And so what you really need to pursue is talk about, well, what does the 2 represent? What does the 4 represent? What if I said to you, what part of the whole thing was colored? Would you give me the same answer? Would you give me a different answer? So taking the answer, which actually kind of makes sense because the kid has a reason to think 2/4, because we've taught them fractions and ratios are the same thing. we know it's not really right with our phrasing of the question, but maybe going at it a different way and kind of respecting the rightness of it and coming at what other fraction could I use rather than thinking about this as being wrong. Now, I wanted to show you one response I got because I've been showing you responses that are problematic. I think one of the things we have to learn to do also is to respond to responses that are fabulous. And I'm going to show you one that I think is fabulous. We asked kids what unit they would use to measure the capacity of a coffee cup, and we gave them a choice of liters or milliliters, and that's one of the expectations that we would be interested in. And we asked them to explain why they did it, and we got a lot of really okay responses, but then we got this response which I thought was so much better than okay. What the child here was doing is not only telling me that liters didn't make sense because those are big and coffee cups are little, but he's actually making an analogy. It's like measuring a pencil with meters. That's a really deep metaphor, a really deep analogy. And sometimes when we get a response like that, another thing that we really need to do, part of our responding to students appropriately, is to find a way to make that student realize how amazing that response actually is. One of the things that I've been talking about a lot is content, but if you read your curriculum document carefully, you'll actually read in the front part that the process expectations, or the processes that we use, are really the heart and soul of the mathematics curriculum. One of the things that maybe we don't do enough is really help our students explicitly focus on those. And I talked to you earlier about creating a great math environment, and I really think attention to the processes is part of creating that environment. So I was trying to think about what could a teacher do to better than saying, well, today we're doing communication. Like, that's not a very engaging way to get into it. What could a teacher do that would get students to explicitly talk about the processes? So I'm going to give you some examples that I think might be fun for you to try. One of them, let's talk about communication first. One of the things that I recalled is that I went to elementary school kind of a long time ago, and I still remember some teachers who would kind of play a game with us. What they would do is they would deliberately do something wrong so that we could catch them. And every single student loved to catch the teacher. And I thought, how could we use this idea in a useful, meaningful way? And I thought maybe we could use this as an idea to get into the processes. So one of the things I was considering is I would help kids think about communication by starting a piece of communication with them and telling them, like, I'm just starting, like, I kind of know it isn't right yet, and I need you to help me. So what I'm going to do is I'm going to talk to, I want to explain to a child why 23 plus 17 has to be 40. So what I said was, well, 23 plus 17 has to be 40 because 3 and 7 is 10. So I think maybe I'm on the right track, but I don't think that explanation's really going to work for him yet. Can you help me? So can you at your tables come up with a way of telling me what's good about that explanation, but telling me what I need to do to really make it better for students? And so it puts the kids in the driver's seat. You're focusing on the communication, but you're making them be the center of attention. It's the students who are going to help you be a better communicator. I tried the same kind of thing with reasoning, and you're going to laugh at this one, but I've actually heard people say this. So people reason, reasoning is a huge part of mathematics, and people often reason poorly. So I'm going to give them an example of me reasoning poorly, and I'm going to ask them to catch me. So here's what I'm going to tell them. So I was telling this other teacher something, and they said I was off, and I just don't get it, so can you help me? So I told them, well, 80 is more than 50, you know that, and 95 is more than 50, you know that, so it must be that 80 is more than 95, because, like, right, they're both more than 50. So what's wrong with that? And she said it's wrong, so help me figure it out. And it sounds silly, and it is silly, But in a way, because it's so silly, kids will get into it. So kids will actually say, well, that was really dumb, and this is what you should do, and this is how to do it. And so engaging them in the reasoning process by having the fun of you being not so perfect. One of the strategies we could use to focus on problem solving, and I actually have seen lots of teachers try this, and it seems to be very successful then, is for you to start a problem, get kids kind of on their way, but ask them to help you finish it. And so, for example, you might be asking kids to solve the problem of find different combinations of two numbers you could add to get 30. So maybe with them, or you could just say, I thought of 20 plus 10, that'll get you 30, and 15 plus 15, well, that'll get you 30, and 20 plus 10, and that'll get you 30, and ask them, how would you finish the problem? Like, what else would you do? Like, how many combinations are there? And ask the kids to finish the problem. And really tell them that I've started you off, but your job is really to focus on how do you solve that problem. And I think that's a probably more familiar strategy to you than maybe what I did with reasoning and communication. One other strategy I wanted to talk about is representation, because one of the things that teachers tell me is that they're really interested in the fact that you can use various manipulatives and various models to show ideas, but they don't always know which is the best way to use which model in which situation. And here, for example, I've seen teachers ask kids to find different ways to represent the number 25, and it's really great. Kids come up with lots of different ways. Some of those ways really help you understand things about 25 one way, and other things really help you understand different things about 25. So for example, I would ask them to represent the 25, and I'd say, okay, so look at your representations. Tell me which of them really help you see that 25 is a 20 and a 5. And what you'll find out is that some of them really show it, and some of them sorta, kinda, but not really. Which of them really help you see that 25 is 5 groups of 5? And you'll find that some of them really do and some of them really don't. And one of the things that's interesting is we often focus on place value representations, and we'll show 2 10s and a 5, and actually that one is maybe a little bit less helpful in seeing that 25 is 5 5s. So all of those things are things to be thinking about when you're thinking about how am I going to focus on the needs of my students. You need to be thinking about the processes as well. Now, I've talked to you a lot about the instructional piece and how in the instruction you might want to differentiate by using open tasks or by using parallel tasks. I think it's important for you to consider that the same would be true in consolidation. That in consolidation you would say, what is the big idea I'm focusing on? Or what is the process that I'm focusing on? And then you would take your practice and you would differentiate your practice in a similar way. So it could be that the big idea appears in different ways. It could be that the process appears in different ways. It's not a bad thing that this student has a different follow-up, a different kind of consolidation than this student. And if in fact the focus is on the process, or if the focus is on that big underlying mathematical idea, you are truly meeting the needs of your curriculum. You are truly teaching to what you're supposed to be. It's hard to summarize this varied path that we've been taking, but I think I want to try to bring us back to the whole idea of what the enterprise is all about. The enterprise of teaching is about the student in front of you. And we are teaching that student. We are teaching the curriculum, but we're teaching it to that student. And our focus needs to be on that student. The curriculum's in the background. It shouldn't be the other way around. It's important, I think, to recognize that not every student needs, and it's not appropriate for every student to get the same task. I think that's critical to meeting the needs of the students in front of us. I think it's also critical to respect the fact that kids need choices. We as adults have lots of choices. Children, to enjoy learning, need some choices. So just like the literacy teacher lets a child go to the library and pick the book that he or she wants to read, we need to sometimes put out an array of problems and let students pick the problem that he or she really wants to do. Now, if we're going to do that, one of the things we need to do is to create a culture of independence. If you look in classrooms around you, you will often see a culture of what I might call dependence. Students are always asking the teacher, how do you want me to do this? What do you want me to do first? What do you want me to do next? And teachers are expecting kids to follow orders in a particular way. And I do think that it is important not to have chaos, and it is important to have an orderly environment, but it is important for students to have a certain level of independence. Whether it's independence in choosing the task they're going to do, whether it's independence, and I'm not going to answer your question the minute you raise your hand, but cultivating that level of independence is absolutely critical to have a differentiated environment, because you're one person and there's lots of them, and you can't get around to everybody unless they are relatively independent. I think there's a mindset issue. The mindset being that I'm there to listen to them, and I have to go to them so that I can move them forward, as opposed to always thinking about bringing them to me as the teacher. And it sounds like that should be obvious, but when we look at our behaviors, I'm not so sure it's obvious. Students have to really believe that you're going to them. And I think we did some examples before where I take a student response and I reply in a more personal way to them. It's critical that we respond to students, that we're listening to what they say and not waiting for somebody to say what I want to hear. I've watched in many classrooms where a teacher asks a question and a kid answers, and everybody in the class knows the teacher isn't like totally happy because she waits and calls on him, not to enrich it, but because I haven't heard what I want to hear yet, and when I hear it, we're done. And it's really critical that what our responses show the student that we're responding to what they've said, not to what we want to hear. I think it's also critical that we provide students opportunities to use the feedback that we do give them. So a student is working on a particular problem and they're struggling and we're helping them, and we give them some feedback. It's our obligation to find another opportunity for students to have another problem where they can actually apply and practice that feedback we gave them, so that that feedback is useful to them. And I think probably for me this is probably, well, the most important message to me is the student front and center, but I guess the other message for me that's so important is that the only way mathematics can possibly be enjoyable to a student is if we allow the part of math that's interesting, which is the part of figuring things out and solving a problem or thinking of a puzzle and how did that work, if we allow access to that for every single student. One of the things we often do is with our struggling students, we are so concerned about the difficulties that they're having, that we scaffold everything. We show them, do this, do this. We have minute little parts for them to do. There is no puzzle left. There is no problem to solve left. It's very uninteresting what we've left for them to do. And so what I think our job in differentiating instruction is to say, here's a student who's at a particular place. They need a problem at a particular level. It's my job to provide a significant, rich problem for those students at that level, not to take a problem that's too hard for them and scaffold it so there's nothing interesting left for them to do. We often talk about our jobs as teachers as delivering the curriculum to students, and the curriculum is our main focus and the students are in the background, and maybe we really have to shift that focus and the students are in the foreground and the curriculum is in the background. And that doesn't diminish the importance of the curriculum. It means that each of those pieces is in its proper place. The other important thing to me is to actually enjoy the potential for diversity in a classroom. I know that we as adults often really enjoy the fact that among a group of friends that we have, different people bring different aspects to our lives. They have they contribute because of their diversity. We talk in the literature about education about the importance of cultivating and embracing diversity, and yet our behaviors don't always show that way. So I really think we do need to embrace diversity, and we really need to truly enjoy it and not really hope that all of our kids are in uniform.
Thank you for joining us for our numeracy webcast, Differentiating Mathematics Instruction. You have experienced some strategies for differentiating mathematics instruction during a problem-solving based lesson or a numeracy learning block. Replay this webcast in its entirety to activate collaborative professional discussion and inquiry about improving mathematics instruction and student learning, or select one aspect of this webcast to study further. Try to implement any strategies illustrated during the webcast within your classroom. Use a job-embedded professional learning framework like co-teaching or teacher inquiry study to enable you and your colleagues to investigate ways to improve your knowledge and skills for differentiating mathematics instruction. Visit www.curriculum.org for a complete listing of archived and upcoming webcasts.